It's my pleasure to have Sam Skalicky present us today about open source deep learning. I've known Sam for a good portion of 8 years, 9 years. I've lost count, I guess. As a undergrad, graduate student, and as a PhD student, he has done some phenomenal work in reconfigurable design. And since then, he has worked in hardware domain, particularly looking at reconfigurable computing at USC, Information Sciences Institute. And he has developed also tools for hardware software co-design at Xilinx before joining Amazon recently as a senior software engineer in their AI and deep learning areas. So today he's here to share with us some of the insights about this open source platform and how we can build projects through this. So with that, Sam, we are looking forward to hearing your insights about this open source platforms.
Great. Thanks for the introduction. Thanks for having me. My background is kind of different, right? I'm not a typical data scientist or machine learning engineer. Most of my training in school has been hardware, but I kind of got into this and it was interesting, so I've been running with it. So I'm going to tell you about some of the work that I've been doing since I joined Amazon. I'm going to keep the content focused on open source and these two projects, MXNet and TVM, and that'll make it easier for me to talk about everything that we're doing at Amazon, but kind of separate the business from the projects. At the end, I'll talk a little bit about what's happening within Amazon in terms of the projects and the structures, and maybe encourage you to come join us. But in the beginning, I wanted to talk about what open source means and kind of walk you through that. So I have a quick agenda here, starting with open source and kind of differentiating open source licensing from organization. I want to talk a little bit about the kind of things you don't think about when you hear deep learning in terms of building your model and training it in a framework like MXNet or TensorFlow. What really happens in the framework? What kind of computations are happening? And how do you translate kind of the architecture of a model and what you learn about when you're learning about how deep learning works to something that you really use in production for training models comprehensively and then deploying them in an application and running inference. And then at the end, we'll talk a little bit about after training. It seems like so much about deep learning starts with, how do I build a model? How should the different layers be connected? What kinds of computation should I do? How fast can I train? Stuff like that. But then that's just the beginning. Once you get your model trained, the hard part really starts then. How do you do optimization? How do you do deployment? How do you manage cost versus performance? All those things. So we'll touch on a little bit of this throughout the talk. So starting with open source, I wanted to start with a definition. So the Open Source Initiative is a nonprofit that's been kind of trying to help organize open source and make it easier for people to understand the different things about licensing and whatnot. And they define open source software as software made by people distributed under a compliant license, which grants rights to use or change or share the software in some form. So when you think about writing some software, when you get something working and you have some code and you're ready to share it with someone, that software is kind of like your product, you own it. And when you share code with someone, you have to think about what does it mean to share it to them, with them. If I give you this code, what do I want you to be allowed to do with it? Do I want you to be allowed to try it? Do I want you to be allowed to include it in your software and then sell it? Do I want you to be able to use it as long as you promise not to sell it to other people? What rights do I want to convey when I share software with you? And that's what open source licensing is all about. So when people say open source, they're typically referring to the specific license for a particular project. And I have a couple listed here. The kind of quintessential open source project has been the Linux kernel. And it's currently licensed with this GNU General Public License version 2. I'm not going to talk about specific licenses, but just to kind of put things in perspective and show you how big open source is. here's a couple more projects. So PyTorch and NumPy are licensed differently. They have this BSD, which is a Berkeley software distribution license. Another deep learning framework, Keras, has an MIT license. And then MXNet and TensorFlow both are licensed with Apache 2.0. So you can kind of see how confusing it could be when you start working on software and trying to distribute a product or a new library or some new model in deep learning. So I wanted to kind of talk a little bit about what does it mean for each of these projects to have a license. So we talked a little bit about if I write some software and I want to give it to you, I need to attach some sort of license to it to kind of set in stone what kind of relationship I want to have with you, how I give you the code, what I expect you to do with it. And so you can think about each of these different projects owning their code, but letting people use it on GitHub under some license. And so if you go to GitHub, most of the time you'll see what the license is for that particular project. So for example, you can look at the MXNet and TensorFlow projects and you can see, hey, they're both Apache licensed, but the projects are run very differently from each other, right? TensorFlow, PyTorch, are run by companies, kind of they own the software themselves, but then they're putting a distribution of it up on GitHub under a particular open source license. Whereas MXNet isn't owned by a particular company. It's a project that's incubating, attempting to become an Apache project. And we'll talk about what that means. But the gist is that the people who own the software and run the project aren't a company, and they're not looking to make a profit on the software like Google is with TensorFlow. So let's kind of switch gears and talk a little bit more about that. So the Apache Software Foundation is another nonprofit that's kind of helping organize how open source projects can be run. So I'm using the term open source project here now instead of open source license to kind of differentiate what does it mean for software to be owned by everyone or owned by no one all at the same time. So the Apache Software Foundation is kind of this decentralized community of developers, right? It's not a business. They're not looking to make money. People who represent the Apache Software Foundation are developers themselves. It's very democratic. People are elected to be in charge. Each project has its own people who are running it, and they're also developers of that particular project. So this kind of differentiates how a company would develop its software and do an open source release of that software online, where these projects are run by the people who are actually working on them, the developers, and they're communicating over these public channels, whether it's a mailing list or a forum or some other, GitHub issues or whatnot to kind of communicate with themselves and with the public. So that really differentiates the motivation and how the projects are kind of run. So I mentioned that MXNet and TVM are, maybe I didn't mention TVM, but TVM is also an Apache project, and they're both trying to become full Apache projects. And the way that Apache does this is they have this incubation period where you apply to become an Apache project. And then you're in this incubator and you're assigned a mentor, and someone kind of helps you organize how to run the project, right? What's the governance of this particular project? How do you do releases? Who's in charge? How do you do releases? How do you manage the licensing for your project in terms of managing the licensing for your software? But then who manages the trademark, the names, right? The logos, that kind of thing. And then through some process over some period of time, you eventually become a full Apache project, and then makes it easier to build this project and software and keep it in the open source domain. So that's kind of where I wanted to start this presentation, but I want to switch gears now and get into the meat of deep learning. But I want to talk about in this presentation kind of the behind the scenes things, the things you don't really think about when you talk about deep learning. So I'm not going to go through a ton of what is deep learning, how do you design a model, what kind of computation is going on, how does it work. I'm going to leave that up to typical um, other deep learning presentations. But I want to start with this fundamental question. What is a deep learning model really? There's a couple of model architectures shown here. You see this multi-layer perceptron on the left with all these layers and these arrows going between layers. And then in the middle, you see a component or a part of something that's called a residual network. And this is something that is used within a model and replicated a bunch of times, and you get this ResNet family of deep learning models. And then on the right, we have two more, just to kind of round things out. Different models with different kind of organizations, and really the kind of things that you're trying to represent here is the computation that's happening. So when you think about a deep learning model, you're trying to take in some data, do some computation so that you can predict some output, right? At the end of the day, that's what you're looking to do. But what does it all really mean in terms of how do I build a model so that I can train it in a real world sense? So let's talk a little bit more about models, right? A model is made up of those layers. So if we go back and we look at the multi-layer perceptron, this is where the word layer comes from. You have all these nodes and these edges between nodes, and things kind of go down one by one. But when you get into more complicated models like this residual network or LSTM, for example, you end up with a lot more nodes and a lot more connections going on, so that things aren't layers anymore. They're kind of a graph, and things can spread out a lot differently. So the word layer kind of only applies to one kind of model, and the word we typically use to represent the computation is an operator. And then the data that you're computing and the interesting data that you're training in order to be able to get your prediction are what we call parameters or weights. So these operators represent the computation. They consume inputs and they produce outputs, and kind of together you build this big network that then is what we call a model. So these parameters and weights are tensors. You can also think of them as arrays. Tensor is just a word that means a multi-dimensional array. Their values are typically randomly initialized and then updated during training. And then these are your kind of secret sauce in terms of these are the numbers that I've used in order to get the prediction accuracy that I want. So inputs to the model are things like images or sentences or other data, whatever you're using, as your input that then you want to predict. So if it's an image, then maybe your output would be a prediction like dog, or if it's a sentence, maybe it's a set of tokens that represent the words in the sentence, right? The input could be something like an audio file or some wave that represents the audio that I'm speaking, and you want to know what are the actual text that I'm saying. So this is like speech to text. But then you also have other things, right? So the computation that you're doing in your model has output, and those output tensors here in red kind of represent the intermediary computation that you don't store. These aren't your weights. These are things that are used during the computation of your model. So thinking about models in terms of a graph, right? So going back to our multi-layer perceptron example, let's look a little bit more about the computation and the operators, right? So in this red box, we're showing a part of the model, the input layer and the hidden layer, and then all those connections between them. And really what this is representing is a operation called fully connected, and kind of the nomenclature should be obvious, right? You have all of your nodes. Each input node is doing some computation for each of the output nodes here, output being hidden layer 1. And then since each input goes to every output, things are kind of fully connected. So that's where the name comes from. But if you think about what we're doing here, we have a 1D array in this example that's 4 elements. And then we have a 1D array for the output, which is 5 elements. And so how do we go from 4 to 5? If you were to count all of those arrows between the two, you'd see that there were 20. And so we'd end up with this weight array, which is 2D, 4 by 5. And the computation that we're doing here, I'm not going to get into the details, but what you're doing basically is a matrix vector multiplication. You're taking that input 4 element, you're multiplying it against this 4x5 weight array, and then you're producing this output. So if we were to take this whole multi-layer perceptron diagram here and kind of turn it into the graph that we would use within a deep learning framework for that model, you'd see what's at the bottom here. So you have your input layer is this green node, and then you're doing a computation to produce the hidden layer, which is our first HL1 red node. And we're using those weights, which really aren't in the diagram, right? But they're represented by each of those arrows. And then we do this a few times, we get our hidden layer 2, and then finally we get our output. So this is the kind of thing where you're translating the type of things that you learn when you're just getting started with machine learning or deep learning, and then translating it into something that you can use in a real world sense to build any kind of model or any size of model, and then train it and deploy it. So one more layer down, I want to talk about the computation that's happening within operators. So sticking with this fully connected example, right? We have our input 1D array, we're going to call that X. We have our weight 2D array, we're going to call that W. And we have our output 1D array, we're going to call that Y. So if we were to change this and kind of look at one operator in isolation, you're going to see this X and W goes into their fully connected, and then it produces some output Y. And so typically you think about this in the forward sense, where X is my input, W is my weight, and I'm going to produce my output Y, right? So that's the forward computation. So you can see we're just doing the W star X to produce that. But then, you know, forward computation is only half of the problem. If you're training, you have to take your particular input, compute all the way through, produce your output, and then you're thinking about, great, I have this output, you know, was it accurate? And if it's not, then you have to compute either some loss or some correction factor to adjust your model so that it's more accurate the next time it sees this input. And this backward computation is still really important, and it's something that deep learning frameworks have to think about on an operator by operator basis. So let's think about backward computation in the context of fully connected. So here, the arrows kind of go backwards. These red arrows here are showing that we are going to take some correction factor y prime. You can call this a derivative if you want. There's all different names for things. And then we're doing the inverse computation to produce the correction factor for each of the inputs to this fully connected operator. So we have a W prime and we have an X prime. And if you look at the backward computation, you can see that to produce each of these correction factors, W prime and X prime, we have to do a separate computation for each one. So we're taking our input Y prime, we're doing a matrix multiplication with the X transpose. Now here, X is our original input. So to do the backward computation, we need to use the same input we used for the forward computation. So we need to keep that around. So that's something to keep in mind as we move through the presentation and think about how the data needs to be stored in a forward pass or a backward pass. And then we do the same thing for the X prime. We're taking our input weight array, we're transposing it, and we're doing another matrix vector multiplication with our Y prime to produce our X prime. So the thing I want you to take away from this slide is just that deep learning frameworks do a lot of computation, and they do it in ways that you don't necessarily think about when you're just building a model and designing the architecture, which operators you should use, and the order and the sizes of the tensors. They do a lot in terms of the forward and backward computation, and they have to do this on an operator by operator basis. Each operator has a separate forward computation from the backward computation, and there's even more things that we'll talk about next. So building back up from the low level of the computation that happens in an operator, each operator has the forward and backward computation like we talked about. But one more thing that you don't normally think about when you're just thinking about the science behind deep learning is when you're building a model, you have these outputs from operators that are inputs to other operators within the model, right? Not your input, not your weight, and not your output, these intermediary tensors. In our original model that we were looking at before, these intermediary tensors are these red nodes, these hidden layers. And so the framework needs to think about things like memory management, memory allocation. And so one thing it has to do is say, given these two input shapes for a fully connected operator, what's the size or shape of the output tensor going to be for that computation? So in our example here, we're giving X as a 4-element 1D array and W as a 4x5 2D array. And the operator needs to tell the framework what size the output should be given those input shapes. So things have to be really generic in terms of when you're implementing an operator. You're not just implementing matrix vector multiplication. You have to implement those backward derivatives. You need to implement functions that just look at what the shapes should be, not doing the computation, just saying if you give me these inputs, I give you this output. And then the framework will go through starting with the sizes of the weights or even just the input and generate and propagate the shapes that need to be used for that computation throughout the model. So building up from operators back to a model, right? A model is really a graph, which is a representation of operators and their data dependencies. And then it's the weights, which are the fixed tensors here. These are the tensors that you're modifying during training to update. But then after training, those values are fixed. And at that point, people start to call them parameters because you're not thinking about the tensor computation anymore. And then models also have inputs, which are the tensors that are provided at runtime. They're not the weights, they're not the params, they're not fixed, right? This is your input image or sentence or whatnot. And so all of these three things, the graph, the weights, the inputs, are kind of what models are made up of. These are the core components. So now that we talked about what a model is and an operator and the computation, let's work backwards up to the top level, right? So let's say I have a model and I'm going to do some training or inference, right? I have my model architecture, I've already designed it. I have the graph that shows the computation and the data dependencies between those computation. That's the graph. So when you're getting ready to load your model in the framework, there's a few steps the framework does under the hood. It loads that graph and it looks at what operators are in it. And it looks at the weights. Maybe your model is already trained and you're loading your pre-trained weights, or in the case of starting from scratch, you're initializing weights to some random value or something, however you wanted to initialize before training. And then you have this next step that we kind of talked about a little bit, where the framework needs to go through and allocate memory to be used for those intermediary tensors between operators, but also for the outputs. Because at this point, we still haven't talked about what outputs are for a model. So based on the input size and shape and the weights shapes, we kind of propagate shapes all the way through the network to get to the output, and then we can allocate the space we need to store the output for the model. So all this, and we haven't even done any computation yet, right? At this point, then, if you were to do an inference on your model, you'd take your input, you'd walk the graph, execute each of the operators, maintain the data dependencies, making sure that you execute the operator to produce the output so that you can execute the next subsequent operator, and so on and so forth until you get to the output. For training, this is where you do the extra step of kind of doing it all backwards again. So you've done your forward pass, you've produced the output. The user then has some loss function or some way to compute a correction factor, and then hands this back to the framework, and the framework kind of works backwards again, taking that correction factor and propagating it back through each of the operators, computing the correction factors for each weight or input, and so on until you get back to the input and update all of your weights. So this is kind of the thing that the framework does under the hood, all of this complexity just to make it easy to build and train and run inference on your models. So this is where I wanted to stop with how things work within the framework. Next, I want to switch gears and talk about, now that I have a model, it's trained, what do I do, and how does the second phase of life for a model go? So after you've trained a model, you have something, you have weights, and now you need to actually take that model and put it in your application and think about how do I actually want to use my model for the purpose that I set out to design it for, right? Whether it's predicting what is in an image or it's identifying movement in a video, right now I need to connect that to my application. So when you think about training versus inference, a lot of the real world examples are showing that training is just this upfront cost. Sure, it takes some time to figure out your model architecture, but maybe you're a company who just wants to do something someone else has already done before. So maybe you're just taking an existing model architecture like ResNet and you're just leveraging it for your specific type of images that you want to predict outputs for. So maybe you train it, maybe you don't spend as much time designing your model architecture, but once you train it, then deploying it into your application, putting it out there for your millions of users that are submitting images on, whatever social media platform, trying to recognize people or faces or things, you're running inference millions of times an hour or a day. And so a lot of the cost of deep learning is on the inference side rather than the training side. When you look at after you've trained your model and you're going to use it for some period of time, maybe a few years, the cost of serving that model on the servers and all of that is much larger than it is for training. So really what you're trying to do on the deployment or inference side is optimize for cost, but of course balance that with your performance needs, right? If you're doing deep learning to kind of estimate, detecting people or stop signs in a video for some self-driving car, you're optimizing for cost, but at the same time, if it can't recognize the person in enough time to avoid it, it's not worth anything. So you kind of have to balance performance and cost in order to have a successful application. So then this is where we get into post-training optimization. So I have an operator, right? We're just doing a bunch of computation now. It's all just a bunch of math to produce the output. And so how can I improve upon my model while still keeping the accuracy that I expect? So there's a few optimizations that you can do on your model after training. And we'll talk about a couple of them, but there's so many more. Probably the most common one for deep learning is called operator fusion. This is where you're merging the compute workload for multiple operators together. So the classic example here on the right, convolution operator produces some output that's consumed by some batch normalization operator. This is kind of the core of, CNNs and residual networks. So if you think about the kind of computation that you're doing here, convolution, is just a form of matrix multiplication. And then batch normalization is kind of an similar kind of thing. But if you think about what you're doing inside of a computer and the hardware architecture, you're loading the input data for this convolution. You're kind of in some sort of fashion reading that data in to your processor, doing the computation, the multiply accumulates, and then you're writing those outputs back out to memory or cache or whatnot. And then you're reading it back in to do batch normalization. So if you think about, the hardware architecture aspects of optimizing that computation, what you want to do is not move your data. So operator fusion allows you to take the computation that you're doing within multiple operators and kind of merge them together so that then you can expose the parallelism that lets you continue to do more computation with less data movement. So if you were to compute a part of the convolution, then you can compute the batch normalization on that output without having to write it back to cache or DRAM, and that improves your performance and efficiency. So, I mean, I don't want to go too much further into the optimization for this one particular operator fusion. There are so many more. When you think about training and your model, you have these weights, you're doing some operators, maybe you're doing something like slicing, you're taking a tensor and kind of splitting it in half, or maybe you're cropping your input image or something like that. Those kind of operations are things that you can kind of do once up front if you're doing it on something like your weight. After training, your weights are fixed. They're never going to change again. So if you can pre-compute any part of the workload within your model, then you can reduce the repetitive computation at inference time. So this pre-computing is something that they call constant propagation, which is not a new thing. It's just kind of done on a different scale within a deep learning model. And then the final thing I want to mention in terms of optimizations is removing the training specific parts. So when you're training your model, you're really kind of trying to introduce randomness into your data so that the model doesn't over train to a particular input. And so you do things like dropout, where you have your tensor and you'll set some of the values within the tensor randomly to 0 or -1 or something. And then that randomness kind of varies with each training pass. That kind of makes your model more sophisticated. Or things like activations, again, where you're trying to add some randomness into your model. So if you remove those, then you don't have to do that computation anymore. That doesn't really impact your overall output or prediction. You can make your model run faster. So let's talk a little bit more about optimization. Constant propagation, I mentioned before, is something that's not new, but it's something that a lot of compilers do under the hood. Whether it's LLVM or something like that, we can then start thinking about compilation at a higher level for deep learning. So there's a ton of deep learning compilers out there. Probably the most common one is XLA, the compiler for TensorFlow, but there's another one called Glow for PyTorch. And then the one that I'm using as my reference point for this is TVM. TVM is unfortunately an acronym with no meaning. I think the guy who first started it, his name was Tianqi, and so it's Tianqi's virtual machine, but TVM really has no interesting meaning for deep learning. But the thing that differentiates TVM from XLA or Glow is that it's not tied to a specific framework. So TVM can take a model from TensorFlow or MXNet or PyTorch or XGBoost or Onyx or Keras and so on and so forth, and extract the computation that's happening within that model in some generic sense, so then it can do an optimization. Right? At the end of the day, convolution in MXNet or TensorFlow or PyTorch is still convolution. So TVM does something interesting where it has this front end that converts your framework-specific model representation into some independent intermediate representation that they're calling relay IR. And then the compiler goes through these phases of optimizing it to produce your final optimized performance executable binary. So after training, you take your model and you'll use this compiler to kind of further optimize it just for inference. The other thing I wanted to point out here is that your model representation is that graph of operators and the actual tensor data, right? The weights. But your model doesn't contain the code necessary to actually execute those operators, right? The code for those operators is within the framework. And the framework loads your model and then executes its optimized routines or functions for each of those operators. But compilation does something slightly different, where after it converts your model to this intermediate representation, it takes the computation for each of those operators and kind of breaks it up from a high level convolution, fully connected, into, you know, small computation that you're doing, maybe loops over some array, and you're doing some multiply accumulate or something. And then kind of at that level, you've kind of gone down from the high level operator into the computation, and you can do more lower level optimization across operators. So deep learning compilers are able to do that operator fusion kind of on a different scale than what the framework can do if it wanted to just optimize for inference, right? The framework at the end of the day still has to execute operators. So someone would have to come in and say, I'm going to write a fused convolution batch storm operator. Great. But then it doesn't optimize for my fully connected followed by, you know, element-wise addition or something like that. Somebody would need to come in and write that specific combination in order for the framework to be able to fuse those operators. But the deep learning compiler takes a different approach. It has an abstract representation of the computation for each operator, and then is able to put this together to do more optimizations globally across operators. Okay, so enough of that detail. So the steps that deep learning compilers go through, they have some front end, they take your model, they turn into some intermediate representation. They're doing some architecture agnostic optimization, things like operator fusion or constant propagation. And then at that point, they're taking that optimized IR and they're handing it to some backend. And the backend could be something like, you know, LLVM or some compiler for, you know, an x86 or some Intel processor. It could be the CUDA compiler for an NVIDIA GPU, or whatever the backend compiler is for the architecture that you're targeting. And then that compiler, that backend compiler itself, has its own architecture specific optimizations. So for x86, this might be something like vectorization. For CUDA, it might be optimizing the computation into different units needed to work within a particular GPU architecture. But then it's producing this executable binary that then no longer looks like the same model that we started with, right? It's code that's been optimized, generated, compiled. You don't necessarily look at that executable and see the individual operators that you started with to represent your model. And even the same thing with the weights. If constant propagation has gone through and you've taken that slicing operator and turned it into two weights, now the weights that you're looking at are totally different as well. Right. So after compilation, then we talk about deployment. So compilation here is just representing the optimization that we're doing for our model post-training. But then let's talk about what it means to deploy a model, whether we've gone through and optimized it with some compiler, or we're just deploying our model with the framework as is. You know, there's a couple of different things to think about when you're deploying a deep learning model for a real world application. So if you have your trained model, again, it's just the graph plus the weights. The framework itself contains the code to execute that graph, and it might support different hardware. Maybe it has routines for CPU or GPU or some custom ASIC accelerator. So it's really easy to take your model around to different hardware platforms and just install the version of the framework for that platform, the GPU version of MXNet or TensorFlow, for example, and then try it on different hardware. This is great. It's easy to try things, but the framework can't be fully optimized for any one platform. It still has to do things generically enough to make it easy to represent the model. But the benefit of this is just like when you were training your model and debugging, you know, the gradients or optimizing for accuracy, it's really easy to look at things and debug because it's the same environment that you were using for training. Compare this with deploying a compiled model. Now it's not a graph plus weights anymore. It's some optimized binary. It includes the code in kind of all inclusive, It's already compiled, which means it only runs on one platform. So if you compiled it for x86, or if you compiled it for, one family of GPU, it won't run anywhere else. So it's really hard to take it around and try it on different things without having to go back. The great thing about this is it's heavily optimized, but that comes with its own constraints. You can't look inside anymore. It's a black box. It's really hard to debug. It's all generated code. You're not looking at operators anymore. You're looking at the computation within an operator that's potentially fused with other code for other operators. And so trying to figure out why you're getting different accuracy in your compiled model on your ARM device, for example, is really different than trying to figure out why you're getting a different answer on your Intel laptop when you're training your model. So deployment has its own pros and cons. But then let's talk about the application level. So I have a model, I trained it on a specific snapshot of data, maybe dogs, and then I deploy my model, but it's in the real world, right? The constraints change. Maybe there's new dog breeds that people start getting. Maybe cameras are different, and so the pictures of dogs are different than the ones that you use to train your model. Maybe people start taking pictures of their dogs sitting down or instead of standing, and so the angle is different and your model is not trained on that specific way dogs look like. And so you kind of constantly have to keep track of how my model ages over time and look at the accuracy of the model. All of a sudden, are the confidence scores for my predictions going down? And if so, maybe I need to retrain my model. And there's all different ways you could do this. If you're looking at confidence scores, maybe you store inputs that produced a poor confidence, so that then when you retrain it, you can use that data to improve the model, all kinds of things. But that's just the model. I mean, it's sitting within some application to do something interesting, right? So sometimes the application needs change. Maybe initially you made this model to identify movement, and then all of a sudden you want to identify people that are moving, not just that something moved. Same thing with classification. Maybe you start classifying dogs, but then, you put a camera outside your house and somebody was walking their cat on a leash, and that's not a dog. So maybe you want to change it so that you can classify all animals and not just dogs. Or one more, speech to text, right? So as I'm talking, if there was some live captioning going on, then you can have a model that turns that into text. But if I say something in a different language, then you start thinking, well, hey, we can do that. What's stopping us from supporting language translation also? Because kind of we're translating audio into text. So you're just different audio into different text, right? So your application needs might change. And this is just the beginning of everything, right? There's all kinds of other constraints that you start thinking about when you're deploying when you're deploying a model. Things like model security. You spent so much time training your model, you've used all these servers and spent so much money to train it to get those specific weight values. You want to make sure that your custom model architecture, the graph, or the specific secret sauce, the weights aren't going to be exposed and someone could just take it and then run away with your model. Kind of security on the opposite side, privacy. Maybe I want to identify people, but I don't want to store their data. So how do I make sure that the picture that I'm running inference on kind of doesn't get stored or sent around to other people? So how does a model kind of ensure the privacy of the input data that it's processing? And then you get into all kinds of things like homomorphic encryption and doing computation on encrypted data. Because at the end of the day, deep learning is just computation, right? So we could go so much further into deployment. But I think this is where we're going to stop. Just to kind of summarize the things that we talked about, we started off with open source licensing and governance, and that licensing for some project isn't the same thing as an open source run project. At the end of the day, you write some software and you give it to someone with a license with an expectation that they're just going to use it like you told them to. And then deep learning projects are open source. So getting into the deep learning side of things, it's really just math, but it's complex. And then a model is really just this program of functions, right? Operators and their data dependencies. And then the framework that you use to build and train your model is this collection of functions that are executed by some runtime engine to compute, the outputs that you're looking for. Compilation is an optimization stage that takes your trained model and then optimizes it for some specific platform, CPU or GPU or some custom accelerator. And then at the end of the day, you're building a model so that you can deploy it in some real world application. So all the constraints that go into deployment and security are stuff that you should keep in mind. So that's the summary, but I would be remiss if I didn't advertise a little bit about Amazon while I'm here and I have your attention. So there's not a lot on this slide. I'm going to say a little bit about what AI at Amazon is. We do a lot of things. It's really broad and deep. So I've, throughout my career at Amazon, worked on different things from the framework, MXNet in this case, but we also have teams that work on different frameworks, PyTorch, TensorFlow. And then we have teams that take those frameworks and build toolkits on top of it, things for doing computer vision or natural language processing to kind of help people in those specific domains build models. And then we have a team that takes the toolkit and kind of builds a service around it. So maybe you've heard of things like recognition, where you submit a picture and they just tell you what's in it. So that's kind of building the deep stack of tools and services. But then things are really broad too. Things like data set labeling, right? You've collected all these images that you want to use to train your model, but somebody needs to go through and manually label them. So doing things like trying to find the ground truth, or using things like Mechanical Turk, which is not a model, right? It's really just people going in and doing the labeling manually. And then all of the things end to end. We have teams that are building little development tools like Deep Lens, which is a camera with a embedded NVIDIA GPU processor that lets you get started with doing CV, to teams working on things like Deep Racer, where it's a little car with an Intel processor in it and a camera, and it's trying to automatically drive around on the road. But really, at the end of the day, Amazon's not tied to any one framework, right? They want people to come with their application and just run it on their servers. So we have everything, and we're not specific to any one platform. So I would encourage you, as you go through your career and think about next steps, to consider Amazon. Here's a little screenshot that shows right now, I took this last night. If you go and search for machine learning jobs, right now there's 4,174. So quite a lot of opportunity for everything from software development to data science to machine learning science, solutions architect, if you just want to build things, and everything in between. So something to keep in mind. And that's it. Thanks so much for your time. I guess we can take some questions.
Thanks, Sam. That was a great introduction to the open source tools. I think a great 101 to a lot of the students. I think there was one question in the chat. Fatima, do you want to ask?
Yeah, hi. It was a very great presentation. So I was curious about the model aging part that you were talking about, that if you see that your model is performing worse and the confidence of some prediction is not so high, you store them and perhaps retrain them. I was curious about how is that confidence measured? Like, how do you know that this prediction has low confidence?
Right. So the standard kind of quintessential computer vision models, the thing that they output isn't really dog, but it's really a set of labels, right? So if you've trained your model to identify 1,000 different animals, it'll tell you which animal it thinks that picture represents, right? And it's not just a 1 and a 0, it's a score. Like, I think this is a dog, it might be some other 4-legged animal, and that confidence for that particular label is what I was referring to. So if you look at the confidence for the outputs for all those labels, and they're all very similar. Maybe you have, I don't know, 3 labels and they're 33% for all 3. You really can't make a distinction between which one the model thinks it is. So you might want to save that data as an example.
Oh, okay, I get it. So the initial computation from the softmax, you kind of see how like how different they are for the different labels.
That's right.
Okay. Oh, thank you.
Sure.
I think another question from Sumin. Sumin, do you want to ask? I can't hear her, so I'll ask the question for her. She says, thank you, it's a nice talk. You mentioned model aging, then how do you retrain your network? Is it fully retrained and deployed again, or train only on new data on top of the existing model?
Yeah, that's a good question. I guess it all depends on what you want to do. If you want to go and start from scratch and retrain, that's something you could do. If you wanted to do incremental training and just kind of think about, when you did your initial training, you had these, I don't know, thousands of images that you went through and did all these training iterations, right? You could just continually do one more iteration with each of the new images that you found to kind of add the correction for that into the whole model. Or, you could use your current weights as a starting point for retraining. Instead of just initializing the model randomly, you could use the current post-training weights as your new starting point for retraining from scratch. There's all kinds of different things you could do. You kind of need to experiment and see which one works best for your application.
Thank you, Sam. I think there's a question from Greg. Greg, do you want to ask?
Yep. Yeah, thanks. I didn't hear the first part of your talk, so I apologize for that. I work at Carnegie Mellon University, and there's a lot of privacy preserving work going on in the model building. When do you think the sorts of things that you're implementing and making available for broader consumption will be practically available? Do you think that's in the next year, or do you think it's further out than that?
It's a good question. I mean, it all depends on what the level of completeness you're looking for. There's people who have been doing research with homomorphic encryption, for years, and just now, in the recent few years, people have been taking that and kind of trying to use that as the way you do computation for deep learning models. I think in terms of there's so many aspects to privacy, right? So it depends on which one you want to talk about, but I think we're going to start to see things roll out. I think just like, machine learning and deep learning has kind of come here with silly little things like hot dog detectors and, identifying dogs, we're going to start seeing small privacy features rolled out over time.
What do you think might be a first privacy feature? Just speculate for me.
I think the simplest thing is to think about, the privacy aspects, or trust is probably the better word that we use in regular computer architecture and operating systems, right? When we boot a computer, how do we know we're booting the trusted operating system? And I think we're going to start something there where you have a camera that takes a picture, that encrypts it, that sends it to some server, that decrypts it, runs the inference, encrypts the result, and sends it back. And it'll just probably start with end-to-end encryption to protect the privacy of the application before it becomes something where you're protecting the privacy of the people that you're taking pictures of.
Yeah, what I was, because what I'd be looking for is, the camera takes the picture, it encrypts it, it sends it off to the server doesn't decrypt it, still classifies it, and sends it back.
Yeah, so that's definitely something that interns at Amazon have been working on for the past few years. A lot of the problem with that, though, is the computation is rather limited in terms of you can do addition or multiplication, but it's hard to take a model.
Yeah. Cool, thank you.
Sure.
Thanks, Greg. I think we have another question from Vedant. Vedant, do you want to ask?
Yeah, hi. Yeah, first of all, great presentation and thanks for the presentation. So I had a question. So in one of the slides you had where the inference cost of inference is like 90% of the training inference, like, but usually it takes 3 times more computation for training compared to the inference, right? So in what terms is it like 90% of the training? Can you explain?
Sure, sure. If you think about, computer vision, right, one of the common data sets people use is this ImageNet data set. And, maybe it's 100 gigabytes of data that you use to train your model with, right? And you run it a few times and maybe you retrain your model 10 times, but then you're going to take that model and deploy it for a year or two. And if people are submitting millions of images a day, that's gigabytes of data per day over however many years, times however many servers you need to process that data in a reasonable time. So if you look at that, things kind of skew towards the inference side in terms of cost.
Okay. So it's for the whole lifetime of the with deployment you're talking about, right?
That's
Of the
right.
model. Okay.
Okay.
Thanks.
Is that clear, Vedant, or you
Yeah.
have questions? Okay. I have one quick question on your, you said the train model versus compile model. You talked about the pros and cons. In what kind of algorithms and tasks do you prefer to use a train model versus in what tasks are you preferring a compile model? What are the main, I mean, if you have to pick like your top application for either of those scenarios, what are those?
Sure. So maybe we can talk a little bit about, edge versus cloud. If you're taking your model and you're going to deploy it into some, embedded camera with a little, NVIDIA GPU or something, maybe the most important things to you are making sure that the model fits. So maybe you want to compile it just so that you get the compression of the weights, or maybe, you only have very limited compute power. And so you need to do the compilation in order for that model to be useful at that scale. Versus in the cloud, you're kind of running a service and you want to make sure that your service is running well. So your needs are more oriented towards logging or traceability in terms of what kind of inputs did somebody submit that caused my model to work incorrectly or produce the wrong outputs or have low confidence scores. And so maybe in that case, you wouldn't use a compiled model, you just use the framework because you have the scale to use a very large GPU to do your acceleration in terms of optimizing it specifically for the one compute workload. So, I mean, it can really go either way. It really depends on what the needs are of the application and then the management of that deployment.
So are you, yeah, I can see that, like, when you're resource constrained, you want to have more optimized model, but not with as many features. But then are you because on the edge now you would want to do a lot of other things because the demand is there right now, right? So are you guys looking at the hybrid models, like where you could still have some kind of flexibility in terms of debugging instead of just have like that rigid model with the compiled version? Are you looking at any hybrid models or no?
Not intentionally, but recently, last night, we completed our deployment for this new service that I've been working on. We have this compiler service within Amazon called SageMaker Neo that kind of runs TVM under the hood. And one thing that I've been working on is how do we compile models that the compiler can't support 100%? And one thing we did is kind of take the model, since it's a graph, and just partition it, compile the components that the compiler can support. So maybe we could use something like that to kind of fit the needs of, I want to optimize this specific part of my model, but then I want to leave this other part of it uncompiled for debugging purposes.
Okay, great. Thank you so much. I think we're right on time. That's a great discussion, Sam. Thank you for taking time and presenting with the matrix.
Absolutely. Thanks for the invitation. It was great being here. Good luck, everybody.
Yeah, bye.